Thank you for the nice introduction. 日本人は日本語でということなので、日本
If you're a Japanese speaker, we have to speak in Japanese. So I was doing this in Japanese. So last year we had two screens. I was able to display both Japanese and English PowerPoints, but I guess this year we only have one slide up. So the slide will be in English. I apologize. So this is the third Q2B in Tokyo, right? And we have been talking here every year, and I have some updates this year again. So let me do that. But I only have 20 minutes, so it will be only partial. But please bear with me. So this is the slide that I always put up as usual. As you know, Fujitsu is a computer company. In 1960s, we have been developing relay method computer. And as you can see, we have FX 1000 existing. So we started FX 10 and FX, this is using Fugatsu. So we have been focusing on HPC technology, but as you have seen from other presentations, computing performance improvement is slowing down actually, because this is the limit of the Moore's law. We're approaching that. So that is why different companies are focusing on applications in order to increase the performance and calculation. That is AI chip as well. So that is why we have been focusing on digital annealer. However, as long as you use silicon chip, at some point in time, we will come to a limit. So that is why we are now working on new computing, and that is quantum computing. A few years ago, we announced this vision, computing as a service. And HPC is only for partial researchers, but we want this to be used at a wider community. And that is why we have HPC and digital annealer platforms. But ultimately, it's not just the experts designating that, but AI will allocate the issues automatically. So this is optimal resource allocation, and that's what the kind of the platform we want to develop. And eventually, we would be using quantum computing there as well. This page is our strategy for quantum computing. So as you can see, we want to go from the software technology, from the application to the software and platform, but it would be difficult for us to do this alone. So that is why we work with different leading world's leading research institutions. Also, in terms of hardware technology, we talked about optical ion trap. There's different types of technologies, and we do not know the ultimate solution yet. So that is why we want to be hardware agnostic as well. And we wanted to cover all hardware, but of course our resources are limited. So we're focusing on just two. One is superconducting qubit with RIKEN, and we do diamond spin qubit with TU Delft. And we're also exploring other possibilities. We have Fujifilm, Tokyo Electron, and TU Delft that we work with in terms of algorithm. And of course, for us, application is most important. So as you can see from this example here, we work with these customers. We had the actual production machine last year, but we actually do collaborations, researches using application as well. And you know this quite well, but last October, we released 64 qubit system, superconductive computer, quantum computer in collaboration with Professor Nakamura. In the opening talk, QCA talk didn't say anything, but last year was actually a very important year. So RIKEN last year developed the first quantum computer, and I think we developed our second domestic quantum computer, and Osaka University, I think, was launched the third. And Japan, we're purchasing, quantum computers from abroad, but we also have technology in Japan domestically that is available, and that's why we need to let this be known as well. So what we released isn't just quantum computing, but this is the hybrid quantum computing platform that we launched. This is 64 qubit superconductor and 40 qubit quantum simulator. So this is APC. So it's a platform made of that. And what we can do is by changing one line, we can use one or the other. But quantum computer has different errors, but we will be able to minimize that. Whether the algorithm is functioning or not, if there's an error or not, we'll be able to confirm that. And also, the current quantum computer has many errors. So unless you combine it with APC, you will not be able to find the good calculations. So normally, this is used in a hybrid manner, but we can make one step forward. So the parts which will be calculated by quantum computing, we can use a simulator as well. So it's a combination of the two techniques. So we use this kind of platform. It says future, but actually these are the partners that we have collaborated in our researches. Going forward, the hybrid quantum applications in various fields will be carried out with these partners. Another topic here, I think that's just last month, we issued this press release. The quantum computer we announced last year was produced with Riken. It was a collaboration, so can be used free of charges. So this is the first order for commercial quantum computing system as a Japanese vendor, and we will be delivering this to AIST. And we're still in the midst of working on this, but it will be delivered early 2025. So I want to talk about our diamond spin technology. We do have a booth as well. So we work with TU Delft and since 2020. So this is looking at the defect of the diamond spin, and we use electron spin. We also use tach spin as well. MV center is a typical defect example. Nitrogen itself has nuclear spin, and carbon around it has 13 isotopes. So there's about 10 or so will be used as a module. And electric spin can be using optical information. So by photo link, we'll be able to scale this. And so this will be advantages for scaling up. So this is basic research that we're carrying out. Furthermore, this is sufficiently low, but even at a relatively high temperature, it's still operable as well. So in this way, we are continuing with research and development in order to scale this. We talked about nitrogen earlier, but actually what we're using is tin-based data. And this is because luminescence efficiency is better than NV center, and also there's stability against charges as well. So that is why we're using this. And the experiment is still at initial stage, but TU Delft, what you can see here is the diamond waveguide. And we will produce this, which is embedded. So as you can see here, the red is you're able to see the luminescence, and you can see the stability of the wave as well. And there's vacancy, and there's also waveguide vacancy as well, and that there's sufficient interaction between the two. And we're doing NV center tests, but we will be replacing this later on using Cairo CMOS. And this is the other topic, ISCC. So this is a semiconductor company, but they have announced cryo CMOS technology. I forgot to mention this earlier, but in this technology, we're trying to do 3D integration on one chip. and there's a layer here, and then there's an optical layer, and then on top of that, there's a magnetic field, and there's a control circuit as well. So to keep it low temperature, and we try to integrate this into one chip. And at the beginning of the year, what we announced was that the first step. So this is the NV center. So let's say here, for example, this is a line for magnetic, and here's an NV center, and then there's a microwave. It vibrates, and this is by applying a magnetic. Um, we have tried to demonstrate that you can see this in diamond spin using Karasimas. This is the first of to be announced in the world. And so far I have talked about hardware, but now I want to talk about application from here. So this is a collaborative research with Fujifilm. This is VQE and this is NISC application. And there's no reference, but we just announced this in a domestic society, and then we will be publishing a paper later on. But Fujifilm is a material manufacturer. And if it's a large molecule, it's difficult to calculate the current HPC, so they want to use quantum computing in the future. So right now, we're looking at how large of the molecule by VQE algorithm, and this is only a simulation stage. But as we see qubit increase, then the parameters will increase, and so optimization will take time, and that's a big issue. And so this is a big issue on the solid side. So this optimization has been improved on this research, and we're using 28 qubit right now so far, but we want to go above 30 qubit in the simulation. This is an example with Tokyo Electron. As you know, they're the semiconductor manufacturing device manufacturer. So they want to simulate the reaction between the surface. So they calculate the surface reaction energy. And so here there's water and liquid. So they want to implement this in the production machine going forward. So in order to find accuracy on VQE, they have to use a lot of kind of long calculations, which is inferior in accuracy. So they want to achieve the accuracy close to UCCD answers and reducing the number of gates. So what we're trying to do is, this is just one example, but this is the effort. They want to be able to do this kind of simulation on the actual production machine. So from here, I only have 6 or 7 minutes. Our ultimate aim is FTQC. NISC is doing this as well, but we want to in the future do FTQC. But today, we're still in NISC age, the classical age. But we're doing superconductive. But in order to go FTQC, we need to do more, implement more resources. So we probably need 1 million qubits. So there's a big gap still. We're only about 100 today. So in the future, we want to go 1 million. So 10,000 or 10 or 100,000. What can we do? Actually, we have to do error correction. Otherwise, the larger the qubits, there's the impact of error. So as we're not able to use this very well. But in order to do FTQC, what we're thinking, the current architecture, we don't has lack qubits. So with the cooperation of Osaka University, we want looking at FTQC in order to develop new architecture. And this is what we announced last year. But up until now, we're using source code. There are 4 gates. This is the conventional architecture. So, C0, logical S, logical H, logical T gates. But logical T gate is non-Clifford, but this is very costly because you need different gate operations. So this is where resource intensive. In order to do qubit calculation, you need to do some recalculation. But there's a lack of accuracy here. So the T is costly, but we have to use this a number of times. So that's why we need more resources. So we want to do something with the logical T. So that is why decided not to use logical T anymore and instead use rotation gate. But the physical rotation gate is being used, so that there's still error, but this is trade-off. So other gates, we can actually correct the errors, but phase rotation gate, we have been able to reduce a little bit of error, but this is a trade-off. So we will allow for error, but we will be able to reduce resources as well. So that's the architecture that we have recommended. And I don't have time to go into the details, but there's a paper published on this. So what happens as a result is there's about 10,000 qubits, physical qubits that we use. And with the conventional architecture, we were only able to express it with a limited qubit, but with the newly developed architecture, we will be actually able to use 64 logical qubits. But we're assuming a very low physical error, so it's not easy. But we're actually making improvements on this architecture so that with a limited resource, we can be able to do practical quantum calculations. So going back, I don't have time, but actually here's phase rotation gate. It's a physical rotation gate. And if you use this, there's error remaining, even if you do different encoding. So if you do 10 to minus 5 error, what happens is that we can correct errors on the other gates, but this gate, we can only use it 10 to 5 times, so 5 trillion times. So within that rotation gate limitations, we have to do physical calculations. Then algorithm needs to be improved. So that's an effort we're doing as well. And I'm really running out of time, but just to give you highlights. So this is what we have published recently as well, but this is calculating the green efficiency. And this is basically using Hamilton simulation. But in order to calculate this function, we have to do Hamilton simulation and a time expansion. And try to approximate this with a quantum gate, then we have this parameter, but if you need a number of gates in order to do that parameter calculation. But with this, we're using we can apply this parameter to a larger parameter. And we have issued a paper on this, but we have half of the qubit and 21th of the circuit depth compared to those of the existing methods. So whatever HB is not good at, we will be able to replace it with this algorithm. And also, this is finite temperature simulation. Connexus is talking about this, but how do we do this efficiently? I think the paper will be published in the near future, but basically the objective is to reduce the number of gates. Maybe we will be able to use this by 1 digit or so. So then we will have this architecture that will be usable and can be implemented in practice. Okay, so I'm going to quickly go through this. This is QCNN, Quantum Convolutional Neural Network. So basically using this QCNN that leverages prior knowledge of quantum data to improve computation efficiency. A QCNN, normally you have the cooling area and convolutional area. Unfortunately, is smaller, but if it's a material, then the unused qubit can be used. So we will be able to reduce resources as a result of that. So we have QCNM, but we're putting a lot of emphasis on this. So we have the Japan team and US team, India team. And as a part of that, just to give you an example of what we do is, this is using quantum autoencoder to denoise. In VQE, normally the quantum state includes noise. With autoencoder, we will be able to eliminate noise. And what is the represented data? That actually doesn't require it. the noise quantum state. So we set the parameters so that we can negatively affect the precision of calculations by putting quantum data. And if we try to align this, we will be able to remove the noise to a certain extent. And finally, just 2 slides. So this is a simulator challenge that we did last year. We're doing it again this year. We just closed it, but we have more than 50 companies that will be participating. And for us alone, application ideas are limited, so we invite everyone to submit ideas. And finally, this is our roadmap. So in next March, we will release a large-scale superconducting quantum computer, 256 qubits. Furthermore, in 2026, so this is fiscal year 2020, we will release a superconducting quantum computer with more than 1,000 qubits. So that I went through very quickly, but this is all from me. Thank you very much for your kind attention.